Anything else to? Okay. Yeah. Well, first of all, I'm super happy to be back. I've been to Ferrara once, and it was a lifetime experience. It was not a summer school, but I had the pleasure to be with the AI community of Italy. And I can only recommend not only the sites, but really try out the pumpkin food. It's really, really amazing. So additionally, I would really like to encourage all of you to make it as interactive as possible. So my goal is that we don't finish my slides, because that means that we got into interaction. Okay, so whenever you have a question, just raise your hand or shout or whatever, get my attention, and let's get into a discussion. Of course, I'm also happy to have discussions over lunch, dinner, or, well, if you figure out what my smartphone number is, call me at night. We will manage somehow. So the first part of this summer school, let's see how we can get it running. So I was originally feeling I should talk about lifted statistical machine learning, and the goal is still to tell you that it's not about just relational and probabilities, although I really like probabilities, but you will also see that there's strong ties to general optimization, very basic techniques of machine learning. But I will also touch upon the very basic stuff, like graphical models, and maybe also give you an interpretation of what lifted actually means, and a connection to tractable inference, and maybe even also some tractable learning, or let's say at least more tractable learning. And I also tried to embed this all a little bit into a vision I have, at least the first part. So if you look at what is currently going on in the world, and in particular about AI and machine learning, then I think many people, and not only me, we have all one big dream in common. And this big dream is that it's not only us or experts that can do machine learning and data science, but actually we would like that almost everyone can turn data into knowledge. Okay, so that's one of my dreams, at least. So in a sense, I'm working on getting rid of myself, which is maybe also nice, because then I can enjoy Ferrara more and have to work less. Huh? Should I start again? Yeah, sure.
Sorry.
So you still see we have to work on technology,
yeah,
to get it easier to run. Okay, so I think everyone should be able to be a statistician or to turn data into knowledge. And so if you have this dream, or if you at least follow me a little bit now for this morning on this track on how we can establish this dream, then this is posing a lot of interesting scientific questions. So if you think about it, I think we have to make machine learning and AI more tractable. So I'm playing with the word tractability here. Sometimes we really follow the very formal definition of what tractability means, and we will come back to that. But you can also just have your intuitive understanding of that. So we want to make it faster, in a sense. If you want to understand data and you have to wait a week, well, for some kind of data, you're happy to wait. For other data, maybe you want to have it more quickly, your result. But then, you know, it's not everything just a single table. So in machine learning, typically we like to have everything into a single table. But this would mean that we just have a single book, in a sense, in a library. And I think you all know that libraries are a little bit more interesting than a single large book. There are many books. Books are referring to each other. So you have to think about more complex data and knowledge, right? How can we get that into? Or if you have maybe followed recent articles in the New York Times, there was a big hype about the recent Google, some people say breakthrough, that they have now the assistant understanding when you want to order or get a reservation at a restaurant. And if you just switch a little bit of context, then these systems still have problems, right? So how can we manage to get machines do that as well? How can we have all this more complex background knowledge involved? But then if you really want to get this, everyone can understand data, then we have to also get machines to understand the type of data automatically and to find the representation of the data automatically. It's related to representation learning and deep learning, but it's also related to just decide on very basic statistical types. So I'm not sure whether you ever had this chance already to have a little bit of a data piece in front of you, and then you wonder, is this one column you're looking at, is that a Gaussian? Is that a Poisson? Is that a generalized gamma or whatever? And these are very tricky questions, even for statisticians. Finally, and there are many, many more, overall, we have to make now sure that you don't need much input from the expert, but then given that we also want to get a partnership with a computer, it's not that you maybe want to have it completely out of the loop, right? So you want to still stay in the loop. And you will have some lectures later also about different aspects of all of these questions. So let me motivate that a little bit more. So indeed, today is the golden area of data. You may feel like that. You can read now even about data and AI and machine learning and science, not only once, but several times. You can have interesting blogs. So everyone is kind of excited about machine learning. At least when I go to companies or to colleagues in different areas, it always feels like this, that they have this single table. And then they say, oh, Kristian, come on, apply some machine learning so that we can maximize revenue, where revenue can now mean whatever, right? So you're a company, you really want to get more money. You're a scientist, you want to have maybe more papers, more insights, whatever. So please apply some machine learning, and now you can choose from the big toolbox of machine learning whatever you want to use. You can use a Gaussian process, you can go for graphical models, boosting. There's a tons of that. But is that really that simple? Is it really that we just have to understand a little bit of a toolbox and apply it, and that's it? So what do you think? Sounds like a cool marketing argument that you just need few algorithms and that's it. Well, my problem with that is that there's a big, what you may call data science loop around it, okay? So typically, and yesterday, I think I worked with two of the students here on the bus, and I had to call my wife because she's a medic and they have to write a proposal, and again, we hit the wall of how many participants in the experiments do I need in order to get this question clear, right? Something a machine learner on average never touches. The machine learner just gets the data, applies a machine learning algorithm, and gets a result. I'm exaggerating a little bit here, and so I apologize to everyone who is also asking the question, how many examples do we need? How do I collect the data? But all science and also all business is starting actually with the question in mind, right? So you're not just getting data out of the blue and then you run a machine learning algorithm and you're happy, but you start with a research question in mind. So that also means that you should think about how to collect data at some point in your life. And that is really changing business, and it's typically not considered in machine learning. So then there's the rather little part of machine learning. So I recall when being at the CPAIOR, which is Constrained Programming AI and Operational Research Conference, there was the Chief Operational Research Officer, in a sense, so the head of operational research at Google. And he was very happy, but also frustrated because of, if you think of his whole job as 100%, then he's spending maybe 5% of his time in a project on solving, and the rest 90 or 95% is about understanding what is the problem, formulating the problem, revising the problem, communicating results, and so on and so on. So the hardcore solving algorithmic part is rather small, and that's quite often in machine learning applications as well. You may have to discuss results, and then if you're lucky, you may deploy. But even on the way there, you have to make so many decisions, like is it a continuous or a discrete or a finite or a categorical random variable. If you have decided on that, you may have to think about what is it actually? Is it a multinomial? Is it a Gaussian? Is it a Poisson? then you have the results, and then actually reporting the results is as important as well. So many of you being PhD students, it's similar to writing a paper. And it's not just dumping results. It's not just saying, oh, I did that, and this is what the outcome is. But you have to think about your audience, and you have to think about what's your takeaway message. And then in many machine learning and data mining approaches, you're not getting just one result, but several of the results. And just dumping all of them to the human doesn't work because the human brain is not working that way, right? So you have to consider that. And then the big question at all, have you found an answer? And maybe you haven't. And then you have to start from the very beginning. Maybe you have to even adapt your question because it turns out that your question is too difficult to answer. So now this is just because, just to illustrate you that there is a lot of work around core questions of what is a good machine learning tool. It's also about how to use it. But even if you have now understood that there's this big cycle around it, the problem is that most data is maybe not in tabular form. So here you see one example, which I'm very happy about because coming from the computer vision community, and in the early days of computer vision, they were very much tabular only. And now actually, if you look at the recent CVPR ICCV papers, you see that they are much more into heavy knowledge-driven tasks. So you see a lot of visual question answering. And here you see the visual genome where they are looking at different images. And now they also extract different objects from the images, and you can now have relations between different objects, right? So it's not just a single table, it's not just a single image, but you have a full graph, and some nodes are images. So how do you deal with that if you have only one single table? If you think about how to represent a graph as a tabular form, that's rather difficult, right? Because whenever you add a node, you are not just changing the number of examples, but you may also add new dimensions, new features. So your table is constantly growing if at all you want to keep everything into a single tabular form. And then if you think about it, and some of my spies at Google, so some of my friends and also some of my students working there, they also tell me that also other companies are now starting to think about oh, damn it, I know that all my data, or most of the data in the world, is stored in a relational database. Right? So why first extracting a single table from it if there are maybe also techniques that can make use of the whole database in there, and by that getting a better view on everything. So if you see who got recently hired also at top positions, you can see clearly that there's this path towards relational representations. So in my opinion, yes, sure, it's the golden area of data, but to be honest, only for the best trained, best funded machine learning and AI teams. And I think we have to change that, right? It's not that it's something that only very well trained and well funded people should be able to use. But I feel like it's very much like knowledge, and there should be a free flow of knowledge, and everyone should do it, should be able to do it. So from that perspective, we really have to think about how to democratize AI, machine learning, and data science. And as I will argue over the lecture, I think we also have to work on what is maybe called systems AI. So it's very unlikely that you can just apply a single machine learning algorithm, but maybe we have to start working on combining different machine learning algorithms to get our overall result. And also in deep learning, you can see that because people are stacking different classifiers together. So now the interesting fact is that relational approaches, as you can see today and the whole week, there you actually have a very natural view on having several classifiers. So what is a problem in first place if you come from a single table is maybe not at all a problem if you just take different tables into account, because then different tables are different classifiers. And as long as they are, for example, giving you probabilistic outcomes, you can imagine to train them jointly and to also learn an overall model. So this is why so many people are excited about relational learning. So let me illustrate that a little bit further, and we will come back to this example then later on, and you will see different ingredients to solve this example more efficiently. So very simple. let's say we want to classify papers into categories, right? So you're a PhD student, you would like to have a good overview of what should I have a look at, what should I read? So you get all these scientific papers, and your question is that machine learning or not, let's say. So in machine learning, one way of doing that, and it's a little bit more classical, although there are some more recent papers showing that there's maybe no, well, there are differences, but they're still very close to also deep learning, and you can have deep versions of that. I'm happy to give you pointers on that offline. But one way, very traditional, is to learn what is called a support vector machine, which you see here below. So you have two classes, let's say only two classes, and you would like to separate them, and you would like to separate them by learning a hyperplane, so a line, essentially, separating these two classes. And in order to be very confident in your classifications, you would like to maximize what is called the margin between the two classes. So you want to get your line in a way that the next examples on each side for each class are furthest away. So you can write down that mathematically. I'm not going with you through how you can arrive at this mathematical formulation, but the main point I want to make here, it's a formula. And many people, or to put it slightly different, even if you like formulas, you can argue that machine learning, that mathematics is definitely not a high-level programming language. So if you want to take this program here and translate it into code, you have to think about how to index, you have to think about what is the meaning of which variable. So you see it's not typed, it's not even close to anything you may know from Java, or if you like, even from Python, although Python is not typed. So there's this gap, right? So typically in the good old days, what you do is you translate that into matrices. And now if you have millions of objects, these one single matrix may get very large. So instead, what you may want to have is a more high-level programming language. Now here specifically tailored towards mathematical programs, where you can write down in a more declarative way, very much like what you have seen here, right? So it's minimization, maximization over some objective function, plus some constraints in here. And now the cool part is you can translate it more or less one-on-one, and then the machine takes care of all the rest. And as long as this language is embedded in Python, you can also connect it with other things. So some of your variables you're using here, for example, could now be produced by another classifier that you have run first. So really, main point is we would like to have high-level languages so that we can stay close between what is written typically on paper form by a mathematician and what you would like to program. And this is only one way in the start, and you can have a lot of different languages and approaches in there. So far, this is just a different way of writing down, and you could say, oh yeah, so what, right? I'm smart enough, I can do it, they should call me, they should pay me, I want to get rich, that's all fine. But now, I was cheating a little bit, right? Because actually, papers are citing each other. And I think if you classify papers, you're not just reading papers, you're making use of additional information. So if you read of your favorite author already the 10th paper, you're expecting that this is again about the same paper topic, right? So if you know that I'm doing machine learning, then in the 10th paper, you're not surprised that I'm doing machine learning. So classification can also become easier because you have already some results. Or if you know that this paper is citing a lot of other machine learning papers, then even without reading the paper, you should have a high prior that this paper is about machine learning. So how can you take these citations into account? So keep in mind, we are back now in the situation that you're not having a single table, but you may have at least another table representing a graph of citations. So how can you make use of that? So the typical approach is to make use of what is called a kernel. So you're trying to embed everything into typically in high dimensional or infinite space, and then you can maybe make use of that there. And if you have a graph, you could use, for example, random walks on the graph. But this is very tricky. So I can only invite you to go to a company and tell them we are using a graph kernel, and let me even explain it to you. So if you're lucky and you can really talk to the CEO, you will have a 1 minute before this guy is falling asleep or telling you, yeah, whatever, tell me, is it really increasing my revenue, right? So instead, now you have a high-level language. What you could also do is you can just add a few lines of codes. And this code is just telling you, if two papers are citing each other, then they should be on the same side of the hyperplane. And adding these 2 or 3 lines is first of all something that you can understand, and if you can understand, and we make it even a little bit easier, then CEOs can understand that easily as well, because you just very naturally say, well, they're citing each other on the same side of the hyperplane, right? So you can try now to even reduce the mathematical load so that other people can understand. And it gives you a growth path for machine learning in general, because we have actually not focused much on the constraints. So typically, machine learning is focusing much on mathematics underlying the model and the algorithms to train these models, but they look at very simple constraints. Now, if you have also a little bit of a background in AI, AI actually likes constraints, and there are whole communities talking about how to make use of constraints. So now getting these two communities together, I think we will have a lot of interesting new, not even so far seen machine learning things ahead. You can also see that already a little bit in robotics, for example. So there's a lot of interest now in safe robotics, because robots and humans have to work together. And so now you would like to have this additional constraint, for example, and yes, it's selling, but let's say never kill a human. So now, how do you train a reinforcement learning algorithm with the additional constraint never kill a human? So it's not as easy. So there are many groups now working on it. Anyhow, constraints, because now humans and machines work much more closely with each other, become much more important. So takeaway message for the first part of for my tutorial, but I hope also for the summer school in general, is that we have to get somehow machine learning, AI, and also in my opinion, but I will not touch much upon them, computational cognitive science closer together, and get a crossover with programming abstraction and data abstractions. We humans can do it, so machines should be able to do that as well. But also for very pragmatic and practical reasons, because if you have high-level languages like the relational stuff, you will see a lot here, then you don't have to talk about all the little details. You can stay at a more abstract level. You can have a more compact encoding. You're getting closer to high-level programming. And by that, I hope we make all of you a little bit more effective in a sense, so even experts more effective. Additionally, what you will see, and I will touch upon that, but I think also Vaishak in the afternoon lecture will tell you a lot about how to make use of these more abstract representations to even speed up. So having an abstract representation and a compact encoding, we will demonstrate that by that you can also get faster machine learning and AI running. And I think that's very exciting. So driven by these two motivations here, there will be two parts essentially in my lecture. One is about lifting probabilistic inference and tractable probabilistic models in a sense. So this is about this part of making everything faster. So we reverse, so to say, the order. And then I give you a little bit of an overview of what statistical relational learning, respectively a little bit of probabilistic programming is, which will then be detailed in the whole week. So let's start with the first part. So who of you actually knows graphical models or probabilistic models? Okay, some, I would say maybe 5 to 10%. So it's maybe good that we recap, and you guys, you control me, right? When I say bullshit, please raise your hand. Let's make it active here. Whenever you see something that is not true, bump me, okay? Kill me. Okay, so first part, as said, it's about graphical models, and we will essentially just touch on the very basic part of graphical models, and then I will show you how to make use of symmetries, and this is the part that is getting maybe the closest to statistical machine learning. And then afterwards, I will show you that all the hype about deep learning can also be carried over, I think at least, I convince you of that, to probabilistic models as well. So, by the way, this guy up here, that's Judah Pearl. Judah was the one, I mean, graphical models got introduced so in, I think it was ecology. But Judah was the one that was pushing it a lot and also putting it into the hands of almost every machine learning AI person. And for that and all his contributions, he got the ACM Turing Award, the Nobel Prize for computer science. And if you ever have the chance to meet him, it's exciting to talk to him. He has a great intuition and can actually also formalize it. But you should also ask him about jazz, because he's a big jazz fan and player. And he may even give you a small jazz jam session, even without the trumpet, because he's then making use of his hands. It's really fun. Okay, so graphical models, every one of you most likely have used them already. They are also used whenever you do a Google search. So parts of the Google search, sure, everyone is saying always PageRank. PageRank is one feature of, I don't know, 180 or even more other features and components. And to glue them together, a major part is also graphical models. Actually, people argue that the quality group, which is the search group in Google, is maybe developing the largest graphical model on Earth. But also, if you have used any of your little assistants, at least in the early days, they use graphical models to get the intention of what you are saying. So it's not only that you have to understand the sentence said, but you also would like to understand, okay, what does this guy actually mean? So Siri, for example, is using HMMs, and also all the deep learning right now, most of them are still following the very basic design principles, but then they encode parts of the graphical model by using deep networks. Anyhow, what is a graphical model on this intuitive level? Because you're not observing the words, right? You only observe something like the phonemes or the acoustic sound here. You have to turn them into words. And so you may think of that the words are producing whatever you hear, and you're encoding that by having for each word a random variable encoded by a note. And then edges are something like this distribution of this random variable, in this case a word, is depending on the previous word, and it's also producing the phone name. And by that you get a temporal ordering here, because you could say that's the first word, second word, and so on, and you may produce from left to right what you have seen, what you have heard here, but you may also go backwards. It's only a way of computation in a sense, as long as time is really not important for your application. Likewise, you can think about images, right? So let's say that you get an image, and I was at a 60th birthday 2 days ago, and I was very bad in taking pictures, so they got all blurred and very bad. And so maybe we can make use now of graphical models to reduce what I did wrong, right? To get rid of that. And a classical question is, typically you have a little bit of noise, and you would like to get now the real image back from that. And so you can again view that as a graphical model, as a probabilistic problem, where you say the true labels I haven't observed, and you only observe noisy variants of the pixels. And then naturally in a picture, you can say that neighboring pixels are in. And so now the difference here, it was directed. Now you see here that you can also have graphical models that are undirected, because maybe it's tricky to decide on, is this pixel influencing this guy, or is this pixel influencing the other guy? You have to pay a price a little bit for being undirected, but that's okay. And so if you go through many of the applications that companies and scientists are using, then actually most of them can be really formalized as a graphical model as dots, which are, or nodes that are random variables, and edges that are encoding dependencies. But actually, as we will see in a minute, it's more about independencies. Anyhow, these are just two very basic examples, so let's go a little bit more into details. So what are graphical models? Well, actually, a graphical model is less about the dependencies, although this is the only thing that you typically see in the first place, but it's actually about independency assumptions that you're encoding, right? So a graphical model, the goal is to encode a probability distribution in a more graphical way, and you do that by making use of independencies, and you try to be more compact by that. Nodes are typically random variables, and edges are coding something like independencies, and you can have directed, sometimes called Bayesian networks, and undirected models, then called often Markov networks, but you can also find random fields and similar names in the literature. And to get both of them together, you can actually also talk about vector graphs, where you code whatever you have to represent here. So here, for example, a conditional distribution, and here just a potential function. You can then give it an extra node and code it there. Less important, at least for my part here. Okay, so let's go step by step now to finally arrive at something that is a graphical model. So we will mainly here at least focus on discrete random variables. So you have a finite set of possible state configurations that a random variable can take on. And the constraints are that the probability of each of these states is greater than or the same or equal to 0. And all the probabilities sum up to 1, right? So we want to have a probability distribution. So examples for that, if you think about smoking and cancer, you can have two random variables. One is smoking, one is cancer. Let's say we have for smoking 3 states or configurations. So you can have not smoking, smoking few cigarettes, smoking many cigarettes, and you have the state for cancer saying no cancer, or you have a friendly cancer, or you have a terrible cancer, right? So this could be one way, but if you start from the very beginning and if you have control about your data, you can also think of other states, okay? So it's up to you, but these are just examples. So is that all what we need? And we have experts in the back, so you should know. And I'm not talking about Vaishak. Vaishak, you can still take a nap if you like. Welcome, by the way. Well, if we want to have a distribution over both of them, yeah, let's say. But whatever you want to do with that, right? Just, we want to talk about both of them and get a distribution over them. So, enough or not? I mean, I interpret what you were saying as not enough, but I'm not sure. Huh? Enough? Should we stop and I hand over to Vaishak because everything is done? Okay, some people are, it's too early in the morning to be active, right? Yeah, it's okay. No, it's not enough, right? So, because actually, as said, as kind of discussed now, we would like to get the joint distribution, right? So we don't want to just talk about smoking and cancer separately, but we would like to talk jointly about both of them. So for that, you need what is called a joint distribution. So joint distribution is not talking about one, well, can also just talk about one, but it's talking typically about more than one random variable, so that you can get the distribution that all of your random variables are into a particular joint distribution or configuration, configuration, right? So you cannot know, you can now not only say what is the probability that I have not cancer, but you can also ask the question, what is the probability that I'm not smoking and I have not cancer, jointly together, right? But otherwise, because you can always put these two random variables together and treat them as a super random variable with the configuration no as one state and no benigna as one state and so on and so on, you know, you still know that all these values should be between 0 and 1 and they should sum up to 1. But you would like to have the joint distribution. So why do you want to have the joint distribution? Because I'm not very often talking about all the configurations, like if I wonder whether you like what I'm saying, I'm not going through all your hats and keep the configuration completely together, but I may just wonder what is Vaishak thinking currently, given that there are people sitting around him, he is influenced by them. So I would like now to go from the joint distribution to a subset, for example, of the random variables. And this is called marginalization. So you have a joint distribution, and now you would like to about few of them only. And in our very simple example, this typically boils down to summing over rows and columns, right? So from the joint distribution, I can get back the distribution of smoking. For that, I only have to get rid of cancer. Well, not in real life, but in my distribution at least. And this means I have to sum, because we have here discrete random variables, but in general you have to integrate over all their values. And if you're in your tabular representation, that means you're just going along all the different states of cancer, sum them together, and you get a probability distribution, which is then corresponding to, in this case, smoking no. So you take 0.768 plus 0.024 plus 0.008, which is 80, which hopefully I was consistent, was 0.8, right? Yeah. So with that, it's already good, because we can talk a lot about now not only all variables, but also subsets of random variables. But you may also want to talk about something like, what is the probability that I am having cancer, given that I know that I'm smoking? You have observed me, well, you will have observed me actually, I guess, in the breaks, that I'm a smoker, so you can then wonder, what is the probability that I also have cancer? By the way, according to my doctor, right now it's 0, but that's a different question. So for doing that, you can now also make use of the product rule or chain rule. So you know you can prove that P of xy, the joint distribution, always factors into the product of P of y, given the conditional distribution of x given y. And you can always choose the order. So you could have said also P of xy equals P of y given x times P of x, right? That's what you see here. So it's always up to you. They are completely identical. But from that, you can now also see what is the more or less definition of this conditional distribution here. You just have to divide by P of y, right? So you move P of y on the left-hand side. So you take the joint distribution, and out of the joint distribution, you take those out where you're not in a particular state for y, and that's dividing by P of y. And so for that, the only constraint is that P of y should be larger than 0, because you're dividing by it. But you can also say, well, that makes semantically sense because I have observed it, right? And by having observed it, if you can observe something that is impossible, that has a probability of 0, you are pretty good, right? So always keep in mind you have observed something, therefore it has at least some probability larger than 0. And with that, you get also then the most important rule, at least for some people, and that's why you see everywhere Bayesian machine learning, Bayesian programs, Bayesian whatever, because if you now take the chain rule, so you have your joint distribution, you apply the chain rule or product rule in both ways, and then you move one of them over here, so you divide by k, which should be C for cancer, and R should be S for smoking, which is Rauchen in German. If you divide by R and you divide by K, then you're getting exactly what more or less the base rule is about. Because then the base rule is telling you that in order to know whether I'm smoking, given that I have cancer, you can then invert and talk about what is the probability that I'm smoking, that I have cancer, given that I'm smoking, which I can evaluate more easily, times the probability of smoking divided by the probability of cancer. And so this is very important and makes the first argument why this is different, particularly to logic. Because in logic, you can't easily invert direction, right? So you have a flow, a notion of flow, a notion of input-output, typically in basic logic. So if you have your knowledge base and you know that something is true, then you're interested in deriving what else is true. Now, if you know what else is true, it's not easy to invert and ask now what should be in general true. So if you know that the grass is wet if it has rained outside, and the grass is wet if there's a sprinkler outside, and now you know that the grass is wet, by logic, you can't tell me now whether the sprinkler was on or whether it was raining, right? So you can only go for the combination, say one of them has to be true, but you can't tell me which of them. So it's a little bit more effort in there, and that's why some people have developed abduction and other reasoning methods in logic, and you get these kinds of things a little bit more for free if you combine with probabilities, which you will see later. So Here are examples where you can now compute all these conditional probabilities. You can go through them. The slides are online, but it's just putting numbers in there. That's not so interesting, and you can do that in all ways. So, big message is you're interested in the joint distribution because as long as you have no zeros in there, you can reason in any direction. You can answer whatever query someone is asking you about your random variables. And that's pretty cool. So, done. Should we now just all go and try to encode the joint distribution as seen? It depends on what the goal is. The goal is to say whether smoking causes cancer or not. No, your goal is you don't know a priori. Look, it's a little bit like in an oral exam. If students come to me and say, please tell me what are the questions, I'm telling them, no, I will not tell you what are the questions because that's the game. You should learn a joint distribution, right? So if you're a company and you're focusing on a very specific task, then this may work sometimes, but then if tomorrow a different customer is coming and saying, look, from your data we can also answer that, you would like to be able to answer that without running now a new experiment, collecting new data, and so on. So you want to have an overall model that is flexible. It's flexible like humans and not flexible like just one question, right? So we are interested in coming up with the joint distribution because you can then answer whatever the question is. So that's our goal. But now the question is, are we done? Because we can now represent everything as a big table, as you have seen so far, where you're just capturing, well, that was not the one. We are just capturing the whole joint distribution. Is that our goal? Yeah, go ahead. Kareem. Exactly. So the problem is that if you just go for a tabular representation, you have a joint, you have a exponential explosion, right? So imagine that you have just random variables that can take the state 0, 1, yes, no, and you have n of them, then you have 2 to the power of n many configurations. In terms of parameters, you may need one parameter less because everything sums to 1, you can use that constraint to always get the last parameter. But overall, you have an exponential blow-up. And this is too much, typically. So now, question is, how can we get rid, how can we reduce, compress the joint distribution, the table, right? And the main point is make use of independencies. So right now, you're focusing on me a little bit, right? So you don't wonder what is going on in the downtown of, let's say, Darmstadt, where I'm coming from. You may not have ever heard of Darmstadt, right? So you're separating whatever is going on completely from what is going on here. So it's independent, and you're making use of that. Or let's say your flight is on Friday or whenever, and you're not thinking about your flight and what can go wrong by flying back, because that's on Friday, but it still exists, right? So if you're interested in a joint distribution, you should always keep that in mind. But for now, we are interested in saying, no, whatever the flight is going on is not under my control, so it's independent. So what is independency? Independency means that if you have a joint distribution, then you can go for the product of the two independent distributions, right? So P of GA, like gender and age, would be then P of G, probability of gender times probability of age. And it's somehow here already you could now, and I was expecting that somehow from the people in the back, you could now kill myself already, because you could argue that there's a dependency apparently between gender and age, because women get on average, at least in Germany, 4 years, 5 years older than males. In particular, if you don't have a husband, it's interesting at the moment that you get one of us, you're losing this advantage, and we gain again. I don't know why. I think you're helping us, you're relaxing us, and we stress you out. I don't know, but it's by statistics. So you may argue that it's not a good example here, but anyhow, let's pretend that age and gender are per se independent, right? Which makes sense somehow, at least for didactical reasons. So now, because you can apply here the chain rule or something you have seen in the base rule, you can also easily see that this is the same as the conditional probability of A given G equals P of A, right? So you're not, if I'm asking what is my gender, you're not paying me any information. You're not hopefully paying me money for if I tell you, look, if you give me $100, I also tell you my gender. If there's anyone that would give me $100 for knowing my gender, to know how old I am, good, because that would be stupid in a sense, right? So it's independency. But it's really just, you divide by P of G, and then you get the definition of conditional independency, so you see that you can transform there. So now the problem is that this kind of, how can I say that, global independency is very rare. Typically, this is not happening, right? Typically, as already seen here a little bit, there are influences. So here we may want to maybe condition on the age range and so on to get it really independent. So global independency, very rare. So instead, you have to go for conditional independencies. And this is what you can find quite often here as well. So your flight back home is, of course, depending on you. Because if you're not arriving there, they will ask, where are you, right? And imagine that you have checked in online already, then they will make an announcement at the airport saying, Kristian, please come to the gate, right? So there are dependencies. They may not stop, but they may delay a little bit, who knows? It was happening on the flight here, but only because there were unfortunately 2 people sitting in the plane on the runway just before start off saying, oh, we are in the wrong plane. We want to go to Leipzig, which is really the other direction. It was really, they had to come now here. It was really terrible for them, I guess. So there are typically dependencies, and so you want to make use of independencies in a more local fashion, right? So you want to get the conditional independency here. And conditional means that you're conditioning on some observations. So here, for example, you could say that overall, if I'm interested in the probability of cancer and computing the probability of cancer from the joint distribution, then if I know smoking, I don't want to pay any more information about age and gender. So you would like to say that P of C given as G and A is equal to P of C given S. So G and A is not giving you any more information. So you can simplify the conditional distribution you have here a lot. And this is what is called conditional independence. And because you have less entries, right? So if you see that as a table, then you're dropping 2 guys. So you're getting a lot reduction. And keep in mind that this table is growing exponential. So likewise, you're getting a kind of exponential reduction here. So you can now imagine that if you make use a lot of conditional independencies, you can hopefully get a more compact representation. So this is then, yeah? Yeah, we will come back to that later. Sure, so for now, so maybe I should repeat, the question was, oh, in reality, if we only have data, where are these edges and nodes in a sense coming from? This is then called structural learning, and we will touch upon that later. But we have first, yeah? Yeah, so wonderful question. So the question is, Kristian, I think your model is wrong because we should have edges from age going to cancer and from gender going to cancer because there are so many cancer forms that are not just about smoking. So if you're younger, for example, then you have also better rates to survey blood cancer and all this. There's, of course, all these influences. I'm agreed. Here we are talking about cancer that is coming from smoking. Okay, so we make a very specific assumption. But even if you see already by the question you were raising, another benefit of graphical models, namely that you can talk about distributions in a very natural way. So you talk about should there be an edge or not, instead of saying, imagine that you see this. So it's not true, but imagine that this is a joint distribution. So now come again and tell me, shouldn't there be an edge between? Right? So you're looking just as a big table, it's also very tricky to model and discuss results and keep the data science cycle in mind that you would like to communicate with the expert. So the graphical representation makes a lot of sense here and helps. Sorry. Yeah. So this is giving us now the first definition of what a Bayesian network is. A Bayesian network is just a directed acyclic graph over a few bunch of random variables. So you see here always an example. To each of the random variables, you're associating a conditional probability distribution of the node given its parents. So you would like to have here, for example, P of n given S, P of H given S, P of S given A and F, and so on and so on. And then the joint distribution, we are not going to prove that here, but you can prove that the joint distribution is then factorizing according to the graph structure. So it's just the multiplication of all of these conditional distributions you have here. And you're making, by using a Bayesian network, you're making a very specific independency assumption. And this independency assumption is essentially telling you that a random variable is independent of its non-descendants given its parents. So, for example, here, H is independent of, for example, N, which is a non-descendant of H, but also of A and F given S. And you can read them off, and from these independencies, you can get a more compact representation, and you can read off other independencies from the network as well. We will not touch upon that. So here's one example now, coming back to our very simplified smoking cancer example. So we could say smoking, if I smoke, this is causing cancer. If you like this causal connection, although be careful, we are just talking about probabilities, and we are just talking about correlations by that. So there's not much causality in a Bayesian network per se. This needs extra effort, and you can again check Judah Pearl's work on causality, but you may also check Meiner and Bernard Schulkopf and many other people working on causality. So causality is one of the big scientific questions in general. Can we reduce the number of experiments to understand causal relationships? Which cancer types do I have to test in order to understand what are the causal relations between whatever I'm doing and cancer and so on. So that's independent of that. So anyhow, you have these two random variables, you draw edges between them, but you now know by drawing an edge, you're actually coding independencies, right? So it's not about dependencies. And then you have to associate conditional distributions according to the graph structure. So in this case, you would have to write down the joint distribution, the kind of prior distribution for smoking, and you have to write down the probability of cancer given smoking. So now in this particular case, you don't see much about it's more compressed representation, right? So if you look at how much you have represented here and how much you would have to represent in the overall joint distribution, not much. But this is only because we were looking at two random variables only, and there's only the case of they're dependent or there's no edge, right? And in no edge, you would get a reduction if that is the independency. If you go for larger networks, you can easily get a much more compact representation of that. But as we discussed already, it depends on your application domain. So there's no free lunch here. If there are dependencies across all random variables in a sense, then you can't avoid writing down different probabilities for each, for the different configurations. Okay, so but pretend that you got a more compact representation. Now, how can we do inference in there? And what is actually inference? So there are different forms of inferences in graphical models, but we are looking here at a probabilistic query. So we are wondering about the probability of a single random variable given some evidence, something I have observed. Now, from the definition of conditional probabilities, we know that we can rewrite this term by the ratio of the joint distribution of X and E and the distribution or the probability of E. Right, and we just have Now, this part here is only to get everything into 0, 1 range again. So getting it into a distribution in a sense. So it's a normalization. So therefore, essentially what you see is we have to compute something like joint distributions. So in order to get these kinds of queries answers, we only have to focus on how to compute joint distributions. And for joint distributions, how can we get this? Well, if we are now interested in just some joint distributions here, we are plugging in the Bayesian network semantics, and then we are doing what we saw already, we do the marginalization, right? Everything we are not interested in, we sum away, we sum out, we integrate out. So this is essentially what you have to do for inference. But now, being a computer scientist, you see that there might be issues, right? So, because this means you always multiply through the whole Bayesian network, right? Because the sum is here, and you always have to multiply through all random variables in here. And that's maybe not the best way to do it, because we know that sum and product can be exchanged. It's now maybe worthwhile to push once in a while the sums. So if we want to get rid of a random variable, and I can do that I should do that as early as possible in order to not always multiply and sum out, keeping that in mind, right? So you would like to push the sum into the product in order to reduce the number of operations you're running, so multiplications and sums. So here's another example. If you are having a larger Bayesian network, again, something about cancer, but also some other things in there, and you're now interested in what is the probability of having lung tumor, and now you would apply the standard formula here, then you would always go over all exponentially many configurations of all possible random variables, then multiply all of them, so it's a lot of work. But now you can push some of the sums, so you can exchange sum and product. And by that, if you do that in a more systematic way, you can reduce the computational burden here, right? Because then you have local multiplications and local sums, and it's natural that this is less work. So here we are using a particular order, and whether you're getting a more compact computation very much depends on the order you're selecting. And the problem is that finding the right order is hard, so even in a formal sense. So it's really almost, in this case, it's not as hard as doing the inference. The inference is even harder, but it takes a lot of time, just to let you know. Anyhow, in this particular case, you can really show that you're getting a more compact representation also in terms of computation. So the algorithm you have just seen, and maybe some people will also talk about that in their lectures and how to make it even more efficient, is called Variableemanation. Some mathematician wouldn't give it a name, but actually there's a lot you can do in terms of data structures to make it rather efficient. It was introduced by Chang and Poole in the, what was it, 90s, right? 94, I guess, it got introduced. Anyhow, this is just the algorithm written down. So essentially what you're doing, you select an ordering, and then you go through all your factors, and you always take the factors that include your current variable you would like to eliminate, and then you multiply those factors together, you sum out your random variable you would like to eliminate. This is what you do here. So you multiply all your factors, you eliminate the one random variable, and then you put the new factor you got there into your list again of factors, eliminating all the other ones, and you iterate. So you see that in each iteration you're getting rid of at least one factor. So you know that you'd terminate at some point. Yeah, and you can prove that it's correct, and you can unfortunately not prove that you're really efficient, but in several cases, depending on your graphical model, you can be much faster. So let's pause a little bit and see what we have learned so far, right? So I hope I have argued well that dealing with uncertainty is good. If you want to represent uncertainties, then one attractive way are probabilities. If you want to have more arguments why, and there are very also strong arguments by Dependency why you should follow probability theory in order to capture uncertainty. And then if you want to code your probability distributions, you can use graphical models, which are all about independencies in order to get hopefully a compact representation of the joint distribution. And then to do inference in that, to compute a distribution of a single variable given some evidence, you can run, for example, Variableemanation. There are tons of other random inference algorithms around. Just ask me offline, I'm happy to provide you links. So you can ask again, in a sense, mission completed, but unfortunately, no. Why? Well, the problem is that inference in Bayesian networks is NP hard, and actually it is sharp P. And you can prove that via a reduction to 3-set. So first of all, who knows what is a reduction? Third, who knows? Second, who knows what I'm talking about here? Third, who can see how this reduction to 3-set could work? Anyhow, there were 2. Complexity theory. Who is a fan of complexity theory? That's my question. Yeah, okay, sure. Okay, let me first, before showing the reduction, go to why you should have a look at some point in your life at complexity theory. So here's the very classical from the Black Book, on complexity by Gary Johnson. So it's a very good book. If you still find it on stock, get one copy. It essentially just explains you very quickly what is complexity theory, and then it just lists you tons of results. So this problem is this complexity class. This problem is this complexity class. So, but in particular, they're giving you this cartoon here why you would like to understand a little bit complexity results. So if you are in a company or you're doing your PhD, right, and then your boss is giving you a job, compute me X, and it takes a lot of time, right? The algorithm you're coming up is so slow that you have to wait, I don't know, 3 or 4 weeks to get an answer. Now your boss is getting annoyed, right? It takes too much time. So now you have different options. You could say, like here, yeah, I don't know, it's maybe just me, maybe I'm too dumb. Then at least when you're in the US, in the fire and hire mentality, they will most likely fire you. Now, if you could say something like, yeah, I'm a little bit smarter, right? So I couldn't find, me personally, I couldn't find a polynomial time algorithm. So then you express already, yeah, you know that you should check for an efficient algorithm, and you have heard of polynomial time algorithms and so on. So it's already good, but still, as you can see, the guy is not very happy, and most likely you're still getting fired. But imagine that you can stand on the shoulders of giants, and you can say, hey, I didn't find a polynomial time algorithm, but no one else can find. Then at least in front of a US court, there's no reason to fire you. Okay, so that's a little bit their argumentation why you should be interested in complexity results. Anyhow, what is the big point? So P means polynomial time. And back in these days, polynomial time was already fast. Nowadays, sometimes even polynomial time is not fast anymore, and you would like to be linear, or you would like to be even sublinear. So there are even machine learning techniques that don't have to touch all data, right? So then you're even faster. But let's see. So P is okay. P with polynomial time, people are happy. Then there is this, what is called not polynomial, in this sense, non-deterministic, sure. But you can say the NP also as the complement to P, so not P in that sense, okay? And then in between, but I'm not going into details, there's this super nice class of algorithms that, or of problems that are really not, well, most likely not in P, and you can always reduce the one problem to the other problem, and that's called this NP complete stuff. Now, the interesting fact is that no one knows whether P equals NP or not, right? So it may also collapse completely. If you manage to prove that all these circles should actually be the same, consider well whether you want to publish or not. But you can get very famous and also very rich. We can also take this offline. I'm not asking you to tell me the proof. I'm happy to join, but that's a different question. Anyhow, this is the biggest question maybe in computer science. So you would be instantly famous, but you would also be instantly followed by CIA and FBI and whatever, because they want to break codes maybe. So anyhow, so this NP stuff is interesting because now the typical goal is that you know that something is hard to compute. And so, for example, one of the mothers of NP hard problems is these three satisfiability. So you would like to have a satisfying configuration for a formula, for a logical formula, where the clauses are only 3 literals long. And for that, you know that it's NP, in NP, it lies in NP. And now what you can do is to reduce, you can turn this logical formula into a Bayesian network. Because then your argument is like that. I take something that I know is hard, and if it takes only polynomial time to turn that into an instance of my own problem, and I can now solve my own problem in polynomial time, imagine, then you would have polynomial reduction plus polynomial runtime. It's a polynomial runtime algorithm, right? So you would have proven that something that got proven already is wrong in a sense. So that's why you always take a problem where you know the complexity and you reduce in polynomial time, you write it into your problem as an instance of your problem, and by that you actually prove that it should have the same complexity as the other one. So you're taking here the 3 side, you code it as a Bayesian network. Let's not go into the details here in the interest of time. And then you're just getting all of that for free. So what have we learned so far? We have learned that Bayesian networks are interesting because they capture joint distributions, they are darks. Unfortunately, inference in them is not easy. And this also tells you inference about probabilities are not easy no matter what representation you're using, right? So even in a deep neural network, talking about probabilities and computing probabilities, if you can at all do it, is not an easy task, right? So it's not a matter of I'm using the wrong representation. You could do Variableemanation, but there are other algorithms for doing inference. We haven't talked much about how to do Bayesian network learning. We will come back to that in the second part of the tutorial. So, stage, we would like to deal with probabilities, but we also know that inference is kind of tough, and therefore also learning, because if you learn, you also have to do inference. So, do you think that there are additional sources of making Bayesian networks more efficient? So here's one example that Guy van der Broek came up with. Well, actually, he got an email from a user of his system. So actually, the user came up with the problem, but I don't know the name of the user. So I'm attributing it to he. So imagine the following. I have a card deck, right? Let's say 52 cards. And I'm turning around the first card, and I'm asking you beforehand, of course, what is the probability of observing an ace? Right, so imagine that you do that several times, right? So then you get a distribution over it. So what is the probability of the first card in a random 52 cards deck is an ace? Yeah. So there are 4 aces, and we have 52 cards, so 4 divided by 52. So big message to keep in mind is you could answer that more or less in a split second, right? Super fast. Now, let's ask the question, how would a graphical model that, a Bayesian network? Okay? So let's see how to do it, and here's one way of modeling, at least from my side. Maybe you can come up with different models, but I'm saying that there are random variables for each value. So diamond 2, diamond 3, and so on, up to some aces at the different positions, right? So you have for each position, you could have each value, right? So you have the card at position 1 is a diamond 2, the card at position 1 is a diamond 3, and so on. And this can be true and false, and you have a distribution over that. Now, we were talking about independencies, right? And we were saying to get a compact representation, we are interested in getting independencies. So what are the independencies in this domain? Tell me. I mean, maybe they are not. I don't know. So. No, but I can also ask you, what is the probability that the second card is an ace? Keep in mind, we would like to be more scientific and really understand everything and not get brittle systems that can break in a split second by just asking the same question in a different way. So let's really say you would like to have a joint distribution here. Okay, so in my opinion, there are no independencies here. That's the main problem, right? So if you know that the first card is not a diamond 2, then the probabilities of all others are changing, right? So in the first row, it's changing because then it cannot be a diamond 2, so the probability for diamond 3 should increase because there are now less many values. Likewise, however, you also know that the last position cannot be a diamond 2, so therefore all the other ones have to increase there as well. So if you write down roughly the graphical model in this domain, it looks like a monolithical block, because I don't want to write down or draw all these edges. Okay, so that's the main problem. There are no independencies. So there are two issues in there. One is, first of all, you don't want to maybe write down all the different rules in there, all the different edges. So there are too many of them. So maybe we would like to have already programming abstraction, as I promised you in the beginning in the motivation. So here you see, for example, if you use something which you may call Markov logic, but it doesn't matter so much about the underlying language, but you're making use of all quantification and logical placeholders, then actually you can just use two rules here to code your domain. And the two rules are just telling you, if you look at the same position and you may get two different cards there, then the two different cards should be already the same card. And if you can find the same card in two different positions, then the two positions should be already identical. And you put them some weight on top. So that's nice, because then you can answer the same question also for a card desk where you have 60 cards or 100 cards or whatever. These two rules remain fixed. So you have a very compact representation. So you get faster modeling, and there's a lot about faster modeling, and I would like to add also your recent book, but I wasn't getting somehow the reference, but there are some books that can tell you about different languages and how to do inference in there. And if you don't like scientific books, which I can also understand, actually quite a number of big companies are investing a lot in there. So actually, the first invest into DeepMind is said to be about 500 million, 800 million bucks. If you take together what companies for now have spent into invest into relational stuff, we are also around half a billion, 800 million. So hopefully we will have the same effect in the long run. But Uber is pushing a lot probabilistic programming. They have their own little language. Apple was pushing a lot first in the beginning by Siri, where they were using our algorithms, but then now they have acquired Chris Ray's stuffs. His company Lattice, Logic Blocks got acquired for, no one knows, but we think 200, 300 million euros. So I'm just saying there's a lot of interest in there. Okay, just already in the modeling, and then of course also in getting it more efficient. Now, coming back to our stuff, just modeling is not enough. We also want to do inference in there. But as said, there are no independencies. So you're fully connected. So you have something like 2 to the power of 2,704 states. And this is way more than there are atoms, at least according to the physics people, more than atoms in the universe. So even if you can come up with a machine that can somehow do reasoning by putting each state on one atom in the universe, you still can't do the inference because you haven't coded your algorithm to do the inference. So it's really a problem you can solve in a split second, but somehow Judah Pearl's Turing Award-winning framework will break down. Isn't that strange? So where did I cheat? What am I missing? What are you missing maybe? And we talked about that already a little bit. Well, I mean, let's put it slightly different, right? I'm asking you for the first card, but I can also ask, as I said already, the second card, right? So you take the first card, put it down again, and then you turn around only the second one. And now the probabilities are not changing, right? It's the very same situation. So what you're not making use of are symmetries. Yeah? Yeah. So, you know, positions and cards are completely exchangeable. It's something where you can see it doesn't really matter. So we should also make use of the symmetries or the higher languages, because I mean, you saw already that we only needed two rules and we are faster. So we should make use of that to speed up inference. So this is my little idea about what is lifted inference. There are other people that are trying to formalize it in a much more rigorous way. So if you follow, for example, Dan Sucho and Guy van der Broek and Manfred Jäger, they would really like to have an exponential reduction. I'm super happy if I just get a reduction in end-to-end time. So, but the main point is big model. The machine is doing some magic. You get a smaller model, and hopefully solving this and solving that, this one is much faster. So that's the rough idea. And so there's different forms of doing this lifting or in making use of these symmetries, but I want to show you a very simple form which helps you understand lifting also not only for probabilistic inference, but also for, as you saw already, for support vector machines. So how can we find symmetries in a graphical model? So here you see a graphical model again, now in this factor representation. So you have three random variables A, B, and C, and two factors F1 and F2. Okay, so now let's say that we are not having any evidence here. So we are just interested in getting the single node marginals, so the probability of over P of A, over B, and over C, right? So we just want to get each, we want to get the distribution for each node. So because we have no evidence, we can treat them a priori without having any information, right? They should be all identical because we don't know, right? They are all having, let's say, two states. I haven't checked their parameters, so I can say they're all the same. And then I can also maybe make the assumption here that these two factors are essentially coding the same information. Let's pretend in this example here. So I can give them a color of blue to code that. So now instead of computing probabilities, what I can do is I can pass on these color labels, right? So I can say, for example, that the factor F1 is capturing red from the two nodes it's communicating with, and then it's sending back this color code to A and B. Likewise, F2 is collecting red from B and red from C, signs by its own color, sends it back. So after one round, what you see now is that A has a communication pattern, so it connected, it's depending on another red guy via blue factor. B is depending on two other red guys, in both cases via blue factor, and C is depending on one red guy depending on the blue factor. Now, what you can see here is that A and B have the same pattern, right? They are indistinguishable. Only B is somehow different because B was communicating or is depending on two other guys. So you can give them accordingly new colors. So let's say A and C are getting red again, and B is getting green, and then you iterate. You do this color passing again, and you collect. So what you will see in this particular case, after the first iteration, colors are not changing anymore. And you have learned something like that A and C are identical, they're indistinguishable in at least the way they would communicate messages. So now I haven't told you that probabilistic inference in an approximate fashion can also be done by sending around messages. This is derived from the Variableemanation algorithm by doing a little bit of dynamic programming and then assuming that you're just running on a tree in a sense. So you're simplifying there. But if you accept that you can send around messages to compute at least approximate distributions or answers, then you can see now that instead of running inference on this guy here, we can also run on this guy here by taking into account that A and C are identical. So you can, in a sense, fold, if you see this guy, you can fold it now this way, and you can put A and C together, right, and pretend that this is one big node. And by that you have reduced, in this example here, the complexity of having a factor graph with 3 random variables to a factor graph with 2 random variables and only 1 factor. And so now on larger methods, you can imagine that this runs even faster. And there are these lifted inference techniques that now try to make use of these symmetries computed in different ways. You may do it by, in some cases, by passing around colors, but you also can do that in a different fashion, and then you get a similar result as you did, that you can answer this cards example in a split second. So just by making use automatically of symmetries. So you can also view it a little bit like standard programming. You write down your programs, and I don't know whether you still get educated in how you should write down loops, for loops. So it's not like you can write them down in any way to get it efficient on your computer, but you should think about when you ask for what control variable. But now compilers are so smart that they take care of that automatically, so they compile into the best order for your program. And so similar here, we would like now to have compilers for machine learning for graphical models that take care of to compile it into the right form that you get efficient inference. Because we believe that it's not the duty of the domain expert to understand computation so well. They should focus on the problem, on the modeling, and the rest should be done by the computer. So in the slides, but I'm not going through it, you will also get now a little bit of math trying to prove or show you, in a sense, why that is working. Unfortunately, that doesn't work for all cases, but it works for what is called map inference. So if you're not interested in probabilities, but you're interested in the most likely configuration given some evidence, so you're interested in a max, argmax over your P of X given evidence, then you can reduce these kinds of questions to problems which you can solve via linear program. So you try to maximize this score here, and the score here is just in a standard way the probability for each node plus pairwise interactions among nodes. And you can make the pairwise interaction without lots of generality, except for some efficiency in coding, but you can always transfer into this representation, and therefore if you're not interested in efficiency, you can always deal with that. And this linear program is giving you now a kind of polytope in there which you relax a little bit, because in the original polytope that's hard, by saying you're not looking at 0, 1 indication, but you're looking at variables between 0 and 1, and so on and so on. And then you can prove a lot in there. I'm not going through all of them, but the interesting fact is that this color passing we have seen is actually giving you a matrix by which you can pre-multiply your linear program, and by that you're reducing your linear program. So you're taking essentially, let's go back so that you can understand the graphics. You're taking essentially your polytope and you're pre-multiplying by this matrix, and by that you're doing a dimensionality reduction. You're projecting onto a smaller polytope, in this case illustrated by the white line here, because you're making use of symmetries, right? So this guy was supposed to be symmetric to this guy is symmetric to this guy, so you're folding it together, and then you may fold it again and fold it again, and so this way you can show that you can reduce the dimensionality of your linear program by doing this color passing, by giving you a connection to the to algebra. I think in the interest of time, I'm not going through the proof. The proof is not so tricky. It just looks a little bit more mathematical. but this is what you get essentially. So you have your polytope, you want to optimize along a particular dimension, and now you can fold again your polytope into a smaller subpolytope, and then on that we can go. So with that, you can be faster. You can show now, because you're algebraic, that you can lift, so you can make use of symmetries in all kinds of different inference algorithms. And you can also come back to our SVM example from the very beginning, and you can show that also for quadratic programs, not only for the linear programs, but also for quadratic programs, this color passing works and gives you a way to make use of symmetries. So these symmetry finding algorithms, this color passing in a slightly different implementation, they are also used by IBM and Gurobi. They have similar techniques implemented in parallel. So just to illustrate you that it's not just about AI, it's not just about relational databases, it's about general interest into in different communities, and wherever you can help quite a lot of different communities. By that you can get really faster, and for example, I think with FreeRAM you will see some examples of being faster. Marco is showing you some examples, not sure about lifted, but definitely about the lifted modeling, being fast in argumentation mining. Fabrizio is giving you great examples there. So just try to extract, and if you don't like relational, that's fine. Always view it as Python code, right? It's less, really, all what you learn here is less about logic only. You can always transfer back also into some imperative languages. So inference and modeling are interesting. We can speed up, we can make use of high-level languages, but they may still be very hard. So in the last part, last part of the first session, I would like to show you that you can also go a slightly different way, because all what we have seen so far is showing that these symmetries, this lifted inference, is all about tractability, right? About making inference faster. So why not directly trying to get something that is fast from the very beginning? And my motivation story for that is this automatic statistician that I have used already. And this is going back to people like Zubin Karamani and Josh Tenenbaum that had this idea of, can we get a system that takes in raw data and gives you back a report, written report, graphics, understanding. So a problem there is that they did it only for regression. So they were not very general. So I would like to have it now for tabular data, and I would like to have it, instead of starting with an empty Jupyter notebook, I would like that the machine is taking data and is producing automatically heat start. It programs you a little bit of your Jupyter notebook so that you get already basic understanding, basic statistics, and so on. And for that, I would like to use deep neural networks, roughly, because they're pretty powerful and they have shown great results. However, there's a problem with deep neural networks. First of all, they don't have really a probabilistic semantics. So even if you put a softmax at the very last layer, that doesn't mean that you have a distribution over your inputs. Also, you make big modeling assumptions. So with the softmax layer, for example, whenever one output dimension goes up, another output dimension has to go down. That's per definition of softmax. So, you know, when you do deep learning, you're doing also maybe probabilistic modeling, but you may make definitely probabilistic assumptions. So also learning takes a lot of time because it's not clear. I mean, right now, most of them use stochastic gradients in different versions. If you have probabilities, you can also make use of the so-called EM algorithm, which is typically faster. So there's maybe also a benefit. But the main point are really the probabilities, and I would like to illustrate this here to you. So if what we did here is we take a multi-layer perceptron and we learn it on MNIST, but we evaluate it on different data sets, okay, which are similar to MNIST in terms of resolution and everything. And what you see here is that you get something like, for a neural network, it's tricky to compute something like a likelihood, but we tried our best to compute something like that. But anyhow, what you see here is that if you train on MNIST, the neural network with high confidence, will start classifying all the rest as it were coming from MNIST as well. So the neural network can't learn the distribution over the different images you're presenting in MNIST. And this is very bad, because if I tell you, look, this is MNIST, and this is one of the other data sets, you would instantly see the different types of distributions in there, and you would say at some point, no, Kristian, I have learned on MNIST. I don't want to make any judgment on the other data sets. So you could do it, others can do it, but deep networks are trained and they go and they say everything is fine. So as said, we would like to have probabilities here as well. What? Was there a question or just a... Okay. We would like to make use of graphical models, but now we would like to borrow the idea of deep networks into graphical models, okay? And there are two very smart and even more smart people, Adnan Darwish and Pedro Domínguez, who did that. And they come up with something you may call deep probabilistic models. You may call it sum product network. Later you will see that it's an arithmetic circuit. So here what you're doing, keep in mind when we were looking at how to do in probabilistic models, we were looking at sums and products, right? So what you see now here is you're just getting a computational graph like in a deep neural network that is now having specific activation functions that are tailored towards sum and products, because we are interested in probabilities, right? So your joint distribution is factored into two mixtures, that is the sum here, that are then coded as products over two different distributions, and so on and so on. If you manage to do that, then you have inference that is linear in the size of this network. So let's go maybe through an example. So and afterwards we can go for the break. So here you have the joint distribution where you have x1 and x2, right? 1, 1, 1, 0, 0, 1, 0, 0, and you have your probabilities here. Now, in order to get that into a computation graph like in deep networks, you can also look at what is called a network polynomial, right? So an equivalent representation of the table here is a polynomial where you just have indicator variables over x1 and x2. And then if both of them are true, you're putting the value of 0.4 in front of it. If only one of them is true, so let's say here x1 is only true, you put 0.2 in front of it, and so on, and you sum. And then you see that you are, in a sense, equivalent, because if you now would like to compute what is the probability of x1 being true and x2 being true, you just have to look at the indicators 1, 1. All the others evaluate to 0, 0, 0, 0. You only get this part in here, and you get as answer 0.4, right? So you can see that you can make it, you can compute essentially the same information as from the joint distribution. So putting just shorthand for the indicator, whether they're true and false, making it a little bit more easier, you can see that you can do now every kind of inference in there. For example, if you would like to capture all those where x1 is 1, right, then you only have to take, for example, if you want to have the distribution, you know that x1 is 1. I think this one is slightly wrong. You only have to take the corresponding indicator variables in a way that you now sum over 0.4 and 0.2. Right, so all can be done by manipulating, let's go back, by manipulating your input variables, which are the indicators, and by that you're propagating probabilities up, and you get the overall probability of your query. And this is exactly what is called a sum product network, and there are, as said, variants of that. So, and it has a long story. The story is mainly pushed by Adnan Darwish, and if you're interested in that, he has very early communications of the ACM overview article, but he has also a more recent one where you can check. Anyhow, you also have a dark, so a directed acyclic graph, but it's now rooted, right? So you know that there are leaves, and you have one particular root you're interested in. Your nodes are sum, product, and indicator variables. And the weights on edges, in particular going into some products, are just weights of mixtures. So it's a very simple form of computation. But why are we interested in that? Well, first of all, these are computation graphs, so you can also compile them directly to FPGAs. And this is very efficient because it can be even more efficient than TensorFlow. And also learning is very simple. But learning we will touch then after the break, because I see Fabrizio needs his coffee. So half an hour, right? Yes. So half an hour, enjoy your coffee break. Don't kill me, Fabrizio.